Hi everyone, welcome to Let's Talk About Data. I'm Sonu Singh, and this is the start of our 12-week data science series. Whether you're a beginner or looking to brush up on your skills, this series is for you. Let's dive into Week 1, Introduction to Data Science. Data science is the art of turning raw data into meaningful insights. It combines programming, statistics, and domain knowledge to solve real-world problems. For example, companies like Netflix use data science to recommend movies, healthcare providers use it to predict disease outbreaks, financial institutions use it to detect fraudulent transactions. In short, data science helps us make smarter decisions by uncovering patterns and trends in data. The data science workflow typically follows these steps. 1. Problem definition. What are we trying to solve? For example, predicting customer churn. 2. Data collection. Gathering raw data from various sources. 3. Data cleaning. Preparing the data for analysis by handling missing values, duplicates, and inconsistencies. 4. Exploratory data analysis, EDA. Understanding the data through summary statistics and visualizations. 5. Modeling. Building predictive models using machine learning algorithms. 6. Evaluation. Testing the model's performance to ensure it's accurate and reliable. 7. Deployment. Putting the model into action, like integrating it into a company's systems. This process is often referred to as CRISP-DM, cross-industry standard process for data mining. Data science is everywhere. Here are a few examples of how it's used in different industries. Healthcare, predicting patient outcomes and personalizing treatment plans. Finance, detecting fraudulent transactions and optimizing investment strategies. Marketing, personalizing customer experiences and predicting sales trends. Sports, analyzing player performance and improving team strategies. These are just a few examples. Data science has countless applications across almost every industry. To get started in data science, you'll need to learn some key tools and technologies. Programming languages, Python and R are the most popular. Data manipulation. Libraries like Pandas and NumPy make it easy to clean and analyze data. Visualization. Tools like Matplotlib and Seaborn help you create stunning visualizations. Machine learning. Libraries like scikit-learn and TensorFlow allow you to build and train models. Don't worry if you're not familiar with these yet. We'll cover them in detail throughout this series. So, why should you learn data science? Here are a few reasons. High demand. Data science is one of the fastest growing fields, with companies across industries looking for skilled professionals. Versatile skills. The skills you learn in data science are applicable in many fields, from healthcare to finance to marketing. Real-world impact. Data science allows you to solve real-world problems and make a difference. Whether you're looking to start a new career or enhance your current skills, data science is a great choice. That's it for Week 1. Here's what's coming up in the next few weeks. Week 2, Python for data science. Week 3, data cleaning and pre-processing. Week 4, exploratory data analysis, EDA. Make sure to subscribe so you don't miss any of the upcoming videos. Thanks for watching. If you found this video helpful, give it a thumbs up and subscribe to the channel. Don't forget to check out the resources on my website, Let's Talk About Data, for more tips and datasets. See you next time. Hey everyone, and welcome back to Let's Talk About Data. Today we're tackling a foundational skill in data science, data cleaning and pre-processing. In the real world, data is rarely perfect. It's often messy, incomplete, and riddled with errors. That's why cleaning and pre-processing are absolutely essential. Think of it as preparing your canvas before you start painting. So, let's get our data ready for analysis. On Let's Talk About Data, today we'll cover why data cleaning is crucial, how to handle missing values effectively, techniques for normalizing and scaling your data, how to identify and deal with outliers, and of course, practical examples you can follow along with. Why is data cleaning so vital? Simply put, clean data leads to better results. It improves the accuracy of your models, reduces bias, and ultimately saves you a lot of time and frustration. Remember the phrase, garbage in, garbage out. Let's start with missing data. It's a very common problem. We have a few options. Deletion, removing rows or columns with missing values. But be careful, you might lose valuable information. Imputation, filling in the missing values. We can use the mean, median, or mode. /backward fill, propagating the last valid value. For example, in Python with pandas, you can use df.dropna to remove rows with missing values. And to fill missing values, you can use df.fillna, mean, df.fillna, df.median, or df.fillna, df.mode. For forward and backward fill, use df.fillna, method equals fill, or df.fillna, method equals fill. Next, normalization and scaling. These techniques bring your data to a standard range. This is important because features with larger values can dominate those with smaller values. Minute. Max scaling. Scales data to a range between 0 and 1. Standardization z-score. Transforms data to have a mean of 0 and a standard deviation of 1. Robust scaling. Less sensitive to outliers. Scikit-learn is your friend here. Using min-max scaler, standard scaler, and robust scaler will allow you to easily perform those actions. Outliers are extreme values that can skew your analysis. We can detect them using visualizations like box plots and scatter plots. IQR method uses the interquartile range. Z-score method measures how many standard deviations a data point is from the mean. Again, Python libraries make this process much easier. Now, let's put it all together. I'll walk you through a practical example, showing you how to load a messy dataset, handle missing data, normalize, scale, and deal with outliers. You can find the dataset in code in the description. Practice along with me, and you'll be cleaning data like a pro. First, let's create a sample dataset with some missing values so we can practice handling them. Sometimes, when missing values are too frequent, it makes sense to remove them. Here's how we can do that. Instead of deleting data, we can replace missing values with meaningful estimates. Mean imputation for numerical data. One common method is using the mean of the column. This works best when data is normally distributed. Median imputation for skewed numerical data. If the data is skewed, using the median is a better approach. Mode imputation for categorical data. For categorical data, we can use the mode most frequent value. Forward fill carries the last known value down the column. This is useful for time series data. Backward fill works in the opposite direction, filling missing values with the next available value. Once missing data is handled, it's often necessary to scale numerical features to improve the performance of machine learning models. Let's look at 3 common scaling techniques. Min-max scaling transforms the data to a range of 0 to 1. It's useful when features have different scales. Standard scaler standardizes the dataset to have a mean of 0 and standard deviation of 1. It's useful when data follows a normal distribution. Outliers can often be spotted using visualizations like scatter plots and box plots. The interquartile range IQR method identifies outliers based on quartiles. The z-score method identifies outliers by measuring how many standard deviations a data point is from the mean. And that's it. We've covered multiple ways to handle missing data, scale numerical features, and detect and handle outliers. Let me know in the comments which method you use the most. Don't forget to like, subscribe, and share. In our next video, we'll dive into exploratory data analysis. See you then. Hey everyone, and welcome back to Let's Talk About Data. And today, we're diving into the exciting world of exploratory data analysis, or ADA. ADA as your data's first date. It's where you get to know your data, find out what makes it tick, and uncover those hidden stories. We'll be using Python to explore, visualize, and understand our data. So, let's put on our detective hats and get started. On Let's Talk About Data, today we'll cover why ADA is absolutely essential, how to calculate and interpret descriptive statistics, creating powerful data visualizations like histograms, scatter plots, and box plots. And, as always, we'll work through some practical examples. First, why is ADA so important? Well, it's like a first impression. It helps us identify patterns and trends, detect outliers, generate hypotheses, and inform feature engineering. In short, it's about getting a feel for your data before diving into modeling. Let's start with descriptive statistics. These are measures that summarize the main features of a dataset. We're talking about mean, median, mode, and standard deviation. We can use pandas to calculate these statistics easily. For example, df.mean, df.median, df.mode, and df.std. The mean tells us the average value, the median tells us the middle value, the mode tells us the most frequent value, and the standard deviation tells us how spread out the data is. Understanding these helps us get a sense of our data's central tendency and variability. Now, let's move on to data visualization. Histograms are great for visualizing the distribution of a single variable. We can create histograms using plt.hist from matplotlib or sns.histplot from Seaborn. They show us how frequently different values occur in our data. Scatter plots are used to visualize the relationship between two numerical variables. We can create scatter plots using plt.scatter or sns.scatterplot. They help us see if there's a correlation or trend between variables. Box plots are great for visualizing the distribution of a variable and identifying outliers. We can create box plots using plt.boxplots or sns.boxplots. They show us the median, quartiles, and potential outliers. Let's put everything together with a practical example. I'll walk you through loading a dataset, calculating descriptive statistics, and creating visualizations. I've provided the dataset in code in the description below. Follow along with me here on Let's Talk About Data, and you'll be able to perform ADA on your own datasets. First, let's import the necessary libraries and load the iris dataset, which contains flower measurements for 3 species, Setosa, Versicolor, and Virginica. The describe function gives us key statistics: mean, median, min, max, and standard deviation. This helps us understand the overall spread of the data. Now, let's create a histogram to see how sepal length is distributed across the dataset. The histogram shows that most flowers have a sepal length between 5 and 6 centimeters, following a roughly normal distribution. The Cadet equals true option adds a smooth density curve, making it easier to spot patterns. Next, let's use a scatter plot to check the relationship between sepal length and width. We'll also color code the species. We see 3 distinct clusters, meaning each species has unique characteristics. There's also a slight negative correlation. As sepal length increases, sepal width decreases slightly. Now, let's visualize petal length with a box plot to identify outliers and variation across species. Each box represents the interquartile range, IQR, where the middle 50% of data points lie. The line inside the box is the median. and dots outside the whiskers are outliers. Notice how Setosa has smaller petal lengths, while Virginica has a wider range. Ada helps uncover patterns, correlations, and outliers before jumping into machine learning. Don't forget to like this video, subscribe to Let's Talk About Data, and share it with your friends. In the next video, we'll dive into the world of machine learning. See you then! Welcome back to Let's Talk About Data. Today, we're diving into machine learning, one of the most powerful fields in data science. By the end of this video, you'll understand what machine learning is, the different types of ML, basic ML algorithms, how to implement a simple ML model in Python. If you're excited, make sure to like this video and subscribe to stay updated. Let's get started. So, what is machine learning? It's a subset of AI that enables computers to learn from data without being explicitly programmed. For example, when Netflix recommends shows to you, or when self-driving cars navigate roads, that's machine learning in action. Key components: data, the foundation of ML, features and labels, inputs and outputs, model, the algorithm that finds patterns, training and testing, learning from data and making predictions. Supervised learning, definition, the model learns from labeled data, examples, spam detection, house price prediction, algorithms, linear regression, decision trees, random forest. Imagine teaching a child to recognize fruits by showing labeled pictures. That's supervised learning. Unsupervised learning, definition, the model finds patterns in unlabeled data, examples, customer segmentation, anomaly detection. Algorithms. K means clustering, principal component analysis, PCA. Think of this as discovering groups of customers with similar buying habits, without labels. Reinforcement learning. Definition, the model learns by trial and error, examples, AlphaGo, autonomous robots, game AI. This is like training a dog using treats. It learns through rewards and penalties. Steps in a machine learning project. 1. Define the problem. What do you want to predict? 2. Collect data. Gather relevant data. 3. Pre-process data. Clean and prepare. 4. Choose a model. Select an algorithm. 5. Train the model. Learn from data. 6. Evaluate and tune. Measure accuracy and improve. 7. Deploy. Use the model in real applications. Example. Predicting house prices. Dataset. House prices dataset. Features. Square footage, number of rooms. Label. Price. Now, let's implement a linear regression model to predict house prices. First, let's import the necessary libraries. These will help us with data handling, visualization, and model building. Pandas for handling datasets. NumPy for numerical operations. Matplotlib.pyplot for visualizing results. sklearn.model_lib for splitting data. sklearn.linear_model for training a regression model. sklearn.metrics for evaluating performance. Now, let's load the dataset and take a quick look at it. We have features like house size, number of rooms, and price. Our goal is to predict the price based on the other features. Before training, we need to clean and pre-process our data. Let's check for missing values. We are selecting size and número as input features, x, and price as our target variable, y. To evaluate our model properly, we divide the dataset into training and testing sets. %80 of the data is used for training, and 20% is set aside for testing. Now, let's train our machine learning model. We'll use a simple linear regression model. The coefficients tell us the weight of each feature in predicting house prices. Let's make predictions using the test data. Here you can see how close our predictions are to the actual values. To check how well our model performs, we use mean absolute error, MA. Lower MA means better accuracy. If our error is high, we might need to improve the model by adding more features or using a more complex algorithm. Finally, let's visualize how well our model is performing by plotting the actual versus predicted values. A perfect model would have all points lying on a straight diagonal line. If the points are scattered, it indicates some prediction errors. Algorithms and applications. Linear regression, predicting house prices. Logistic regression, spam detection. Decision trees, loan approval. Random forest, fraud detection. K-means clustering, customer segmentation. PCA, dimensionality reduction. Final recap. Great job making it this far. Today, we covered what machine learning is and why it's powerful, different types of ML, supervised, unsupervised, and reinforcement learning, the ML workflow from defining the problem to deployment, build a simple ML model in Python. Next time, we'll dive into supervised learning, where we'll explore regression versus classification in depth, build models like logistic regression and random forest, learn how to evaluate model performance with accuracy, precision, and recall. Try tweaking today's ML model, experiment with different datasets, post your findings in the comments. Don't forget to like, subscribe, and hit the bell so you don't miss week 6. See you next time on Let's Talk About Data. Welcome back to Let's Talk About Data. In this video, we're taking a deep dive into supervised learning, one of the most widely used techniques in machine learning. By the end of this session, you'll understand the fundamentals of supervised learning, key algorithms like linear regression and decision trees, model evaluation metrics, and how to build a supervised model in Python. If you're learning a lot from these videos, don't forget to like, comment, and subscribe. Let's get into it. Supervised learning is when the model learns from labeled data, meaning the input data is paired with the correct output. Examples: spam email detection, label, spam/not spam, house price prediction, label, price. Key concepts: 1. Input features, X. 2. Output/target, labels, Y. 3. Training data versus test data. Types of supervised learning. 1. Regression. Predicts continuous values. Example, house price prediction. 2. Classification. Predicts categories. Example, email is spam or not. Key supervised learning algorithms. 1. Linear regression. Simple yet powerful for predicting numeric values. 2. Logistic regression. For binary classification, spam or not spam. 3. Decision trees. Tree-like structure for decision-making. 4. Random forest. Ensemble of decision trees. Evaluating supervised models. 1. For regression, mean absolute error, MAE, mean squared error, MSE, R squared score. 2. For classification, accuracy, precision, recall, F1 score. Hands-on Python demo, classification model. Great work! You've built your first classification model. Summary. Supervised learning uses labeled data. Two main types, regression and classification. Evaluating models is crucial to understand performance. Hands-on practice is key. Next week, we'll explore unsupervised learning, where the model finds hidden patterns in data. See you in week 7 on Let's Talk About Data. Welcome back to Let's Talk About Data. This week, we're diving deep into unsupervised learning, a powerful approach used to discover hidden patterns in data without labeled outcomes. In this episode, you'll learn what unsupervised learning is and why it's important, clustering and dimensionality reduction techniques, algorithms like K-means and PCA, and how to implement clustering with Python. If you're learning something new, don't forget to like, share, and subscribe. Let's explore the hidden structures of your data. What is unsupervised learning? Unsupervised learning means the model is given unlabeled data and its task is to find patterns, structures, or groupings. Examples: customer segmentation, topic modeling in NLP, market basket analysis. Key concepts: 1. Input features only, no labels. 2. Pattern discovery and grouping. 3. Common tasks, clustering and dimensionality reduction. Clustering techniques. K-means clustering divides data into K-groups based on feature similarity. Centroids, distance calculation, iterative updates. Hierarchical clustering builds nested clusters using dendrograms. Agglomerative versus divisive methods. Dimensionality reduction techniques. PCA, principal component analysis, reduces the number of features while preserving variance, helps in visualization and speeds up model training. TSNE, great for visualizing high-dimensional data in 2D/3D, applications of unsupervised learning. Real-world use cases, recommendation systems, Netflix, Amazon, market segmentation, anomaly detection in finance, document clustering, news or research papers. Now, let's dive into the code. We'll start by loading our dataset, exploring its structure, and preparing it for clustering. Then we'll apply the K-means algorithm and visualize the results. To keep things simple, I've prepared a Jupyter notebook with all the steps, and you can follow along by downloading the dataset and code from the description below. This dataset contains customer information from them all, including customer ID, unique ID assigned to each customer, gender, male or female, age, customer's age, annual income, $, the annual income in thousands of dollars, spending score, 1 to 100, score assigned based on spending behavior, importing necessary libraries. Loading and exploring the data. Here's a glimpse of our data. We'll focus on annual income and spending score to perform clustering. Visualizing the data. This scatter plot shows how customers are distributed based on income and spending habits. But we need a way to identify clear segments. Finding the optimal number of clusters, elbow method. Before applying k-means, we need to determine the optimal number of clusters, k. We use the elbow method. This graph represents WCSS within cluster sum of squares against different k values. The elbow in the curve indicates the optimal k value, usually where the drop in WCSS starts slowing down. In our case, the elbow appears around k equals 3 or 4, so we'll use k equals 3 for better segmentation. Applying k means clustering. Now, each customer is assigned to one of 3 clusters. Let's visualize them. Visualizing the clusters. Each color represents a different customer segment, and the yellow X marks the cluster centroids. This segmentation helps businesses tailor marketing strategies to each group. Wrap-up, and what's next? Summary. Unsupervised learning equals no labels, just patterns. Key techniques: clustering and dimensionality reduction. Useful in many domains, from marketing to security. Next week, we're diving into model selection and tuning. Stay tuned for Week 8 on Let's Talk About Data. Welcome back to Let's Talk About Data. This week, we're diving into model selection and tuning, two of the most important steps in creating a successful machine learning model. In this episode, you'll learn how to choose the right model for your problem, techniques for hyperparameter tuning to optimize performance, cross-validation and evaluation methods to ensure your model generalizes well. If you're excited to master model selection and tuning, don't forget to like, share, and subscribe. Let's get started. Model selection is the process of choosing the most appropriate machine learning algorithm for your problem based on the dataset and the task at hand. Factors to consider when selecting a model: data type, categorical, numerical, time series, etc., size of the dataset, problem type, classification, regression, clustering. Common models and their use cases. Linear regression, used for predicting continuous values, for example, house prices. Logistic regression, used for binary classification, for example, spam versus not spam. Decision trees and random forests, used for both classification and regression with nonlinear relationships. Support vector machines, SVM, used for classification tasks, especially in high-dimensional spaces. Hyperparameters are parameters that are not learned from the data but are set before training. Examples include the number of trees in a random forest, the learning rate in gradient descent, or the depth of a decision tree. Techniques for hyperparameter tuning. Grid search exhaustively searches through a specified set of hyperparameters. Random search samples hyperparameters randomly and can be more efficient. Bayesian optimization, a probabilistic model-based method for finding optimal hyperparameters. What is cross-validation? Cross-validation is the technique used to assess how well a machine learning model generalizes to unseen data. K-fold cross-validation splits the data into K parts. The model is trained K times, each time using K-1 parts of the data and testing on the remaining part. Evaluation metrics: accuracy, proportion of correctly predicted instances, precision, recall, and F1 score, important for imbalanced datasets. Mean squared error, MSE, for regression tasks. Tuning a random forest model using grid search and cross-validation. Importing necessary libraries. Random forest classifier. This is a machine learning model used for classification tasks. It's part of the ensemble module in sklearn, which combines multiple decision trees to make predictions. Grid search CV. This is used for hyperparameter tuning. It performs an exhaustive search over a specified parameter grid and finds the best combination of hyperparameters based on cross-validation. Load under iris. This loads the iris dataset, which is a simple and well-known dataset used for classification tasks. Loading the data. Load under iris. Loads the iris dataset, which contains features, data.data, and the target labels, data.target. Uppercase X, the feature matrix containing the input variables, sepal length, sepal width, petal length, and petal width. Lowercase y, the target variable, which contains the classes, species of iris. Defining the model and hyperparameters. Model. We create an instance of random forest classifier, which is the model we want to train. Param_grid. This dictionary defines the hyperparameters that we want to tune. And underscore estimators, the number of trees in the forest. We are testing two values, 100 and 200. Max under depth, the maximum depth of the trees. We are testing two values, 10 and 20. Performing grid search. Grid search CV. This performs the grid search with cross-validation. Estimator equals model, specifies the model to be used for training. Random forest classifier. Param_grid equals param_grid, specifies the grid of hyperparameters to search over. CV equals 5. This means 5-fold cross-validation will be used to evaluate the model performance with different hyperparameters. This divides the dataset into 5 parts, trains the model 5 times, and uses different parts for testing. Grid_search.fit uppercase X, lowercase y. This fits the model to the data, performing the grid search over the hyperparameters. It will try all combinations of the specified hyperparameters and find the best one. Printing the results. Grid_search.best_. This gives the combination of hyperparameters n_estimators and max_ that resulted in the best model performance. Grid_search best_. This gives the best score achieved during the grid search using cross-validation. What happens during grid search? Cross-validation, the dataset is split into 5 subsets, since CV equals 5, and for each combination of hyperparameters, the model is trained 5 times, 1 for each fold, and evaluated. Hyperparameter combinations. It tests all combinations of n_estimators and max_depth in the param_grid. In this case, there are 2 values for n_estimators, 100, 200, and 2 values for max_depth, 10, 20, so it will evaluate 4 combinations in total. Best parameters and score. It selects the combination of parameters that provides the best cross-validation score and outputs them. This means that using 200 trees, n_estimators equals 200, and a maximum depth of 20 for each tree resulted in the best performance on this dataset, with a cross-validation score of approximately 96.67%. You've just tuned your first model using grid search. Summary. Model selection is all about choosing the right algorithm based on the dataset and task. Hyperparameter tuning helps optimize model performance, and cross-validation ensures generalization. We used grid search to fine-tune our random forest model. Next week, we'll dive into big data in the cloud and explore how cloud platforms handle massive datasets. Stay tuned for week 9 on Let's Talk About Data. Hey data enthusiasts, welcome back to Let's Talk About Data. Today's episode is all about big data and cloud computing, the backbone of how companies like Netflix, Amazon, and Spotify operate at scale. We'll break down what big data means, explore tools like Hadoop and Spark, and look at how cloud platforms like AWS, Azure, and Google Cloud help scale data science workflows. Let's get started. What is big data? Big data equals data that is too vast or complex for traditional tools. We often describe it with the 5 V's: volume, velocity, variety, veracity, and value. Big data tools. Hadoop. Hadoop is an open-source framework for storing and processing massive datasets via distributed computing. Apache Spark. Spark processes data faster than Hadoop thanks to in-memory computing. What is cloud computing? Cloud computing means storing and accessing services over the internet instead of your local computer. Big data plus cloud equals perfect match. Storing big data on the cloud means we can scale quickly, store petabytes easily, and analyze data in real time. Let's do a quick hands-on demo using AWS S3 and Athena. We'll analyze e-commerce sales using AWS S3 and Athena. We'll upload a dataset, query it in real time, and generate insights, all without setting up any servers. Here's our dataset: e-commerce_sales_.csv. It includes order IDs, dates, customer IDs, product info, categories, quantity, price, region, and total revenue. Step 1. Log into AWS and head to S3. Create a new bucket. I'll call mine Big Data Week 9 Demo. Then upload the CSV file to this bucket. Now go to the Athena console. First, configure the query result location in S3. Then, create a database or use default. Let's create a table with this query. With the table ready, let's run some SQL queries to gain insights. Total sales by region. This shows total revenue from each region. Top 5 best-selling products. Here are the top performing products based on quantity sold. You've just performed serverless real-time analysis of sales data using S3 and Athena, no infrastructure setup needed. These skills are used by analysts and data engineers every day to work with big data. To recap, big data is massive, complex data. Tools like Hadoop and Spark help us manage it. Cloud platforms like AWS and Azure give us the power to process it. Next week in Week 10, we'll explore data science in the real world, looking at how Netflix, Spotify, and Amazon apply data science daily. Like the video? Smash that like button. Comment below what tool you want to deep dive into next. And don't forget to subscribe and turn on that bell. Week 10 is going to be Welcome to Week 10 of the Data Science series on Let's Talk About Data. Today, we dive into how data science works in the real world, powering your movie suggestions, online shopping, and even your music playlists. From Netflix to Amazon to Spotify, let's break it down. Netflix uses advanced collaborative filtering and matrix factorization to recommend what you might like next. They analyze your viewing history, compare it with similar users, and even track how long you watch a show. Key tech: Python, Spark, AWS, implicit feedback models. Amazon leverages predictive analytics to optimize pricing, forecast demand, and personalize your shopping experience. They use customer segmentation, real-time inventory analysis, and A/B testing, all driven by big data. Spotify analyzes audio signals like tempo, energy, and danceability. Combined with collaborative filtering, it powers personalized playlists like Discover Weekly. They even use natural language processing to mine blogs and reviews to discover rising artists. Data in the real world is messy. You face challenges like missing and inconsistent data, scalability and latency issues, bias in data leading to unfair models, ethical concerns around privacy and transparency. Real-world data science isn't just code, it's problem-solving at scale. AI can amplify bias if we're not careful. Models must be auditable and explainable. Data collection should respect user privacy. Fairness and transparency are no longer optional, they're essential. Now that you understand how these companies use data science, let's roll up our sleeves and do what they do. I've picked 3 awesome mini projects you can try at home, using free datasets from Kaggle. Let's start with Netflix. Want to recommend shows like Stranger Things? We'll build a content-based recommender system using show metadata. Load Netflix shows dataset. Combine relevant text fields. TF, IDF vectorization. Compute cosine similarity. Function to get recommendations. Example usage. Now onto Amazon product reviews. We'll use NLP to classify whether a review is positive or negative. Load dataset. Convert score to binary sentiment. Text pre-processing and split. Train classifier. Report. Finally, let's decode Spotify. Every time you get a chill vibes or party mix playlist, that's machine learning behind the scenes. Load the dataset. Select numeric audio features. Standardize the features. Reduce dimensions for visualization. Apply k-means clustering. Plot results. These 3 mini projects bring real-world data science to your laptop. They're perfect for your portfolio, and even better, you can build on them to create smarter systems. In week 11, we'll explore how to build your own data science portfolio with real projects and tips to stand out. Hit that like, subscribe, and turn on the notification bell so you don't miss it. Drop a comment. Which company's data science inspires you most? Hey data enthusiasts, welcome back to Let's Talk About Data. We're in week 11 of our 12-week data science journey. And today is one of the most important episodes yet: how to build an impressive data science portfolio. If you're serious about landing a job or freelance work in this field, a solid portfolio is your golden ticket. Make sure to like, subscribe, and hit the bell icon so you don't miss our final episode next week on careers in data science. Also, leave a comment below about what projects you're most proud of. Resumes tell, but portfolios show. When you apply for a job, showing your actual work sets you apart. A portfolio is proof of your skill, passion, and consistency. Google the LinkedIn profile of a data scientist you admire. See if they link to any portfolios or GitHub. Note what makes them stand out. Your portfolio should be clean, easy to navigate, and showcase variety. Ideally, you should cover a few key types of projects. Must-have sections: About Me, projects, at least 3 to 5, blog or articles, optional, contact, resume. Now let's talk about what kind of projects should be in your portfolio. 1. Exploratory data analysis, EDA. Example, Titanic dataset analysis. Tools, Python, Pandas, Matplotlib. 2. Machine learning project. Example, loan default prediction. Tools, scikit-learn, XGBoost. 3. Real-time dashboard. Example, Power BI or Tableau dashboards. 4. End-to-end project. Example, Spotify data analysis or Amazon review sentiment analysis. 5. Web scraping or API integration. Example, scraping job listings using Beautiful Soup. If you want full code for any of these projects, check the description box. We've linked everything. GitHub is your best friend. It shows version control, collaboration, and project structure. Tips: write a clear README with project goals, steps, and results. Use folders wisely: data, scripts, notebooks, results. Pin your top 3 to 6 repositories. Drop your GitHub username in the comments. Let the community check out your work and give feedback. Want to look super professional? Create your own portfolio website. Options: GitHub pages, free, easy, Wix, WordPress, Webflow, drag and drop, custom built using React/HTML. Start a GitHub page right now. Even if it's just one project for now, it's your first step. Having projects is one thing, being able to explain them is another. Practice talking about your role, your thinking process, and your impact. Tips: use the STAR method: situation, task, action, result. Explain tools and why you chose them. Reflect on challenges and improvements. So that was your complete guide to building a killer data science portfolio. You now have everything you need to show the world what you're capable of. Leave a comment with the link to your portfolio or GitHub so we can all support each other. And don't forget to subscribe. Our final episode next week is Careers in Data Science. We'll talk job roles, salaries, interviews, and growth tips. Don't miss it. Pick one project idea from today and start it right now. Share your progress in the comments or tag us on social. Welcome to the final episode of our 12-week data science series on Let's Talk About Data. This week, we're answering the big question: what's next? How do you turn your skills into a career? Think of data science as a tree. From the same roots, you can grow into different branches. Data analyst, data scientist, machine learning engineer, data engineer, BI developer, and even AI researcher. Pause this video and comment below. Which career path are you most excited about? Each role demands a unique skill stack. A data analyst leans on SQL, Excel, and Power BI. A data scientist dives deep into machine learning and statistics. Know your destination to plan your toolkit. Download our free cheat sheet from the description to match skills with your dream job. Your resume is your first impression. Make it clear, project-focused, and keyword-optimized. LinkedIn, that's your 24/7 networking assistant. Take 5 minutes after this video to update your LinkedIn headline to Aspiring Data Scientist, Python, SQL, ML, Portfolio and Bio. Tag us on LinkedIn using #Let'sTalkAboutData and we'll feature the best ones. Go beyond the obvious. Apply smart, filter by skill, tailor your resume, and most importantly, apply consistently. Drop your favorite job site in the comments. We're building a community list. Can't find a job yet? Create your own opportunities. Freelance projects build credibility. Contributing to GitHub builds trust. Try adding a GitHub issue or making a PR today. Start small. Maybe fix a README. Learning never stops, but don't let that overwhelm you. Build, apply, share, repeat. That's how you grow. You've reached the end of our 12-week data science journey, but really, this is the beginning of your story. Subscribe, share your journey in the comments, and don't forget to tag us when you land your first data role. Thanks for learning with Let's Talk About Data. See you in the next series.